Okay, any questions on that? Okay, so here I have another example of that. Let's look at this. So I've got, so first of all, can you sketch these two surfaces that I wrote up there? Z equals radical x squared plus y squared, and z equals 1 plus y. Could you sketch both of those and try to kind of just, first, maybe just imagine or sketch what the space curve of intersection of those two surfaces would be? What's that first thing? Half cone opening where? Positive z-axis. Okay, second thing is a line. It's a line in space. That's what it is, a line in space. No. This is not the equation of a line, right? Equation of a line is a vector. That's a space curve. So that's a vector function or parametric equations. What is z equals 1 plus y? Okay, what kind of cylinder, right? Yeah, so you can, if x is gone, so you could think of it like a cylinder, that's fine. Take the line, z equals 1 plus y, extend it in the x direction, and what will you get? Plane, right? That's plane. So what are we going to get? We've got this plane cutting through this cone. So what is the intersection of those two? Can you see that? See the intersection right here, looking down on it. And then I'll highlight it here. Okay, so we want to write that's a parabola, it's on an angle, right? So it's like an angled parabola, or something, we think it might be an angled parabola. How are we going to write the space curve for that? So, we see the x squared plus y squared. Are we going to let x and y be cosine and sine? What we're really looking for is, when we do cosine and sine, is that cosine squared t plus sine squared t equals 1. So cosine squared plus sine squared equals z squared. That doesn't really work with this. Okay, what about, but z equals 1 plus y, right? Yes. So we can combine these equations and we get 1 plus y equals, right? And how can we make heads or tails of this? Square both sides. Okay, so now this has potential to use cosine and sine, okay? Because we could be looking at the equation of what? When we multiply everything out and regroup. Circle. Maybe, okay, because we've got x squared and y squared terms. So this is potentially a circle, but maybe not. So we have to kind of chase it out. So what do we have on the left? 1 plus 2y plus y squared equals. So look, the y squareds go away, and so now we don't have a circle anymore. If those y squareds wouldn't have gone away, we would have had a circle, and we would have been using cosine and sine eventually. But the y squareds go away, and now it's just what? Y equals x squared minus 1 over 2. So now I have y equals x squared minus 1 over 2, and I have z equals 1 plus y. So how are we going to parameterize this? So we're not going to use sine and cosine because we don't have a circle, right? We don't have a circle in any two of the variables. We don't have a circle. So what are we going to do? So what we can do is strategically let one variable just be t. Okay, just let one of them be t. So what should be t? If we let x be t, then we'd have y in terms of t, and then we could easily have z in terms of t. Do you see that? So if I let x be t, then what's y? T squared minus 1 over 2. And what is z? Now z equals 1 plus y. So 1 plus y. Done. Do you see what happened? So that vector equation is the space curve for my yellow angled, and it is indeed a parabola. Okay. Did I lose you? So when we were at this step right here, that potentially could have been a circle, but when we chased it out, the y squareds went away. The y squareds went away, and that became in the xy plane a parabola. And so no circle, so I can let x be t and y be t squared. Then y is naturally, touch it, stop. All right, and then y would be t squared minus 1 over 2, and if we know y, then we know z is just 1 plus y. 1 plus y. And so we've written all three components in terms of t. Any questions on that one? So now, if say it was z plus 1/2 y, or let's do 1/3. And turn this off. Then what? So the ellipse. See, if it's but the way it was before, that angle of that plane was parallel to the angle of the side of the cone when it was just 1 plus y. See how that angle of that plane is parallel to the edge of the cone, and that's why it just was a parabola extending. But if you have a shallower angle on that plane, like 1/3, then what do you get? You get an ellipse. See that? So you could start the same way. You'd have 1 plus 1/3 squared, and then when you get to this step, the y squareds aren't going to go away. And you're going to have a circular or an elliptical equation. And you're going to employ cosine and sine. Because in the xy plane, you're going to have cosine and sine to write that elliptical curve. So that would be good. You could finish that one at home if you want to do that. Make a sketch of that and change it to z equals 1 plus 1/3 y, and see how the math turns out differently. Because you're going to actually, in this part right here, you're actually going to get the equation of an ellipse and not a parabola. And then you're going to use sine and cosine in the x and y coordinates to write that ellipse. And then z will still be, whatever you have for y, you'll just do 1 plus 1/3, whatever you have for y. And that'll be your z coordinate, or component. So you could practice that one at home, or we could do it in office hours. Let's do another one, though. Any questions on this one? When you see x squared plus y squared equals 16, it should be like fireworks, like, oh my gosh, I know what that is, and I know how to write that with x and y and t. Yes? No? We saw it like 3 times today. so far? Maybe this will help. If you look straight down the z-axis, maybe that'll help. Looking straight down on the xy plane.
Because your x squared is my x substitute x squared with 4 cosine t. So that would just be 4 cosine t. Why? Maybe I'm wrong. Yeah, very.
No, I don't think I'm right. Square equals 4.
Oh my gosh, you guys.
Accidentally, yeah, I got stuck.
Okay, thank you.
Okay. Yeah, so you have to but no, please explain it. Not the whole thing, just this.
This is my last hint. How do you express in x and y a circle with a radius? In this case, the radius is 4. Last hint. The circle is radius 4, centered at the origin. How do you express that in terms of x and y? No, it's not. It's not a question. It's a hint. It's not a question to answer. Okay, last minute. Last minute.
I don't think it's x squared. I don't think 4 is squared. The reason is because 4 is radius, and radius is 4, not 16. So x squared equals 4. So it would just be 2 cosine x would be x. Sorry. Oh, because 1 is the radius, right? And 1 squared is the diagonal. So right now, when you write 1 squared, you're saying like the radius is 1. Yeah. Okay, what I was thinking like also is 4 cosine. So when take the square root, I take the whole thing, so that would be 2 cosine. That's what my.
Okay, ready to go on? Are we good? Okay, so let's talk just more about vector functions. So I gave you this example before. So here's a vector function, one of my favorites. So x is cosine t, y is this polynomial, and z is 0.5 sine 5t. And remember, if you put all those vectors as position vectors, then you sweep out a space curve. So here's that space curve swept out when you let t increase and all your vectors are position vectors. Okay, now I'm going to show you another vector, but now I'm going to put the tail of that vector at the tip of our R vector. And I want you to kind of observe this. It's blue there, see it? And I want you to make observations about this blue vector. So it's another set of vectors, so it's a vector function. So what observations do you make about this blue vector? What's one thing that you notice about the blue vector? So it's perpendicular to the space curve. Is that true? Is it perpendicular to the space curve? The direction of the space curve. It's always pointing the current direction of the space curve. Do we agree with that? Yep, okay, so that's one observation. And so that's direction. So the direction of it is, it's always pointing like where the space curve is just about to go in the next moment, right? Or it's going at that moment. Is the magnitude constant or changing?
Changing.
Okay, so can we try to see how is it changing? So it's smaller now. Smaller now. Now it's starting to get a little bigger. Now it's getting really big. And it's really big at the beginning and getting shorter. What do you think this could be? Yeah.
It almost looks like it's showing the rate of change for as the curve is getting drawn out.
Okay, so is it a rate of change? So how much the curve is getting drawn out with respect to what? Okay, so it's how much curve you get with respect to how much t changes, right? So on that loop there, what's happening? T is constantly. I have t changing at a constant rate. So t is just increasing steadily. So how much curve do you get on that loop for increases in t? Right. So during this loop, you're getting small changes in the curve for the same changes in t, compared to at the beginning and the end, for the same changes in t, you're getting what? Large sweeps of the curve. And so that length of that vector is, yeah, it's a rate of change. It's the rate of change of the curve being swept out with respect to t, changes in t. All right, so what set of vectors is this, do you suppose? Based on those two things, it's pointing the direction of the curve, and it's giving us, its magnitude is giving us the rate of change of curve swept out with respect to t. Yeah? I saw him first, sorry, go ahead.
I think it's the derivative of x, y, and z in respect to t.
Derivative, what were we going to say? Yeah, so you're looking at the derivative of this vector function. It's a new vector function. It's a new set of vectors that's showing us the direction of the curve, just like it's analogous to R2. And the magnitudes of those vectors are how much curve you get with respect to how much t changes. So, can you find it? So this is R. What I'm showing you with a blue vector is R prime t. And so it's exactly what you think it is to find that vector function. So find it, exactly what you think it is. What is it? Right? It's a new vector function, but we don't put this as a position vector. We put its tail always on the current point on the curve. And then that is a lot more descriptive than to show this one as position vectors, right? So what's the x component of r prime? Negative sine t. What is the y component? It's just what you think it should be, right? Just take the individual derivatives of each component. I think this is 2.5 cosine 5t, is that right?
Yep. Yep.
That's a 5. So chain rule, right? Derivative of sine 5t will be cosine 5t times 5 times the rate of change of the inner function, right? So that 5 times 0.5 gives you the 2.5. So a very common application of these vector functions for space curves would be that r would be position, right? So not always, but t would be time. So position at time t. It's a common application, but it's not, when you see RT, you don't have to, it's not necessarily going to be position at time t, but it's a very common application. So you have something flying around in space, so this is its position at time t. So what did we just find when we did r prime of t?
Velocity.
Velocity vector, right? Because the magnitude is what? Or the direction is the direction of the velocity. So let me write it out. So r prime of t then is equal to v t. Direction of v of t is, very simply, think of this as something flying through space, right? Like a particle or a amusement park ride or something like that. So the direction of this is? Direction you're going, right? Direction that you're going at that moment. It's pointing in the direction you're going at that moment. Magnitude is? What do we call that? Speed. How fast? Right? Because if it's how much curve is swept out with respect to t, well, that's how much distance you're going to sweep out with respect to time. That's speed. So the magnitude of the v function is speed. Okay, what am I showing you now? It's the red vector. The acceleration? What do you notice about this one? Constant magnitude. In what direction?
Same direction we're going.
So what vector is this? Unit vector of the derivative. So some of you said v, some of you said the direction. Right. So this is the unitized version of r prime, or of v. This is called the unit tangent vector. So the unitized version of v, or r prime, is called the unit tangent, and it's capital T. We'll talk more about that Thursday. So capital T is, how would I write that mathematically then? Yeah, so I'll use r prime, okay? So yes, it would be, that was right, but I'll just use r prime because that's generically correct. It'd be r prime t over magnitude r prime t. This is called the unit tangent vector. It only gives us it only gives us the direction information about r prime, because it's always magnitude 1. Okay, here's a new one. Orange. Besides crazy, what is it?
That's the acceleration. Yeah,
This is the second derivative. This is the second derivative. And what would it be if it's if R is a position vector? This is acceleration. And why is it so crazy? There's a reason why it's so crazy. There is a reason why it's so crazy. It doesn't seem to have any particular direction. It's the direction is always wavering relative to the curve, and certainly its length is wavering. And so why is this acceleration so crazy? There's a reason. Yeah, in the back. No, so its direction is always kind of different relative to those two. So I'm showing you the original vector r and the unit tangent, which is like the direction of v. And it always has a direction kind of, that direction is not really being consistent relative to those two. Do you see that? It's all over the place.
Like, if you're riding a roller coaster, it kind of looks like the g-force is the direction of the g's that you'd be pulling. If you went in a loop, it force you back into your seat.
Okay.
So,
Okay. Other thoughts, Mark?
It points to the inside of the curve.
Not always. It's yeah, two hands.
As the SR prime t increases, the direction of R double prime t gets either closer to it, or I mean, because of parallelism in general, something that I noticed.
Okay, so
When R prime t is sort of constant, is a constant magnitude, it seems orthogonal to it.
okay, so yeah, I think you're getting onto it. The reason is because acceleration has two components. There's two reasons that you could accelerate. There's the easy way, right? So acceleration, just speeding up or slowing down. That's acceleration. But then there's something else that causes acceleration. Turning. Well, no, that was changing velocity is what I said at first. So yeah, changing velocities, changing speed causes acceleration, but then just turning causes acceleration. So when you put those two together, so what are we doing? So we've got a crazy combination of that, right? So slowing down and then all of a sudden turning really sharply, and then heading straight, not so fast. I mean, so I've got all these different combinations of turning and varying speed. That's why this thing is going crazy. So to make heads or tails of this, we want to break it up into two components. One component is in the direction of the red vector. It's in the direction of t. And that's the acceleration due to just changing speed. Okay? The component of A in the direction of t is just the due to changing speed. Then there's another component of A always pointing at the center of rotation when you're turning. That's called the normal component of A. Normal to the curve, pointing inward to the center of curvature. So that's the acceleration due to turning. So this R double prime is kind of hard to just by itself. So we can find it easily, right? It'd be what? Negative cosine 12t squared minus 24t plus 6. And then negative, what's that? 12.5 sine 5t or whatever. Just take the derivative again, you get R double prime t. But it's not very useful in that form. We want to then break that into components. The component in the direction of t, capital T, acceleration due to speeding up and slowing down, and then in the direction of the center of curvature, which is the other component, which is the acceleration due to turning. But we're going to do that later. We won't do that today. Okay? Okay, another thing that you can do, and we're not going to really talk about meaning, we'll just do the example, is antiderivative or integral of a vector function. And again, that's exactly what you think it should be. Get this out of the way so we can have a meaning for that. Now, it doesn't, if R is a position vector function, this is kind of elusive what this would mean, antiderivatives. So this is just purely for algebraic kind of, this exists. You can take the antiderivative of a vector function, but we're really not getting into the meaning of it. So in this case, it would be sine t. Is that it? Just sine t? Nope. Plus c1. 1/5 t to the 5th minus t to the 4th plus t cubed minus t. Is that it? Plus c2. And then negative cosine 5t. And I think it's is at 0.1. So working backwards with the chain rule, right? So we're thinking what function's derivative would be 0.5 sine 5t. So cosine 5t, they're going to need a 1/5 and a negative. Plus c3. Then if I had a particular vector of this integral function, call this one, I don't know, call it A. No, don't call it A. Call this capital R of t, whatever that is. If I had some particular vector, capital RT, I could solve for then C1, C2, and C3, right? If you knew at some value of t what this capital vector R was, that would determine what your three constants were. Make sense? You could solve for that. Okay, questions on that stuff. So you have somewhat lengthy web work for Thursday. Get started on it tonight, okay?